In the fourth and last part of the lesson, we will study rainfall runoff modeling. We will consider the watershed as a hydrologic system, and we will cover three methods to do rainfall runoff modeling. As we mentioned at the beginning of the lesson, streamflow discharge prediction is one of the most important applications of hydrology, not only to predict peaks, but also to determine the instant of occurrence of the peak, as well as to determine the volume of water that is going to cross some predefined section. The models that allow to compute the hydrograph response from rainfall information are known as rainfall runoff models. Ideally, these models should simulate all the processes that intervene in the movement of water from the surface of the soil to the stream. The simulation of the underlying physical processes is important for predicting stream flow responses under conditions different from the ones for which we have recorded experience. So, simulating these physical processes helps to better simulate the response to never before seen rainfall extremes, to changes in land use in the watershed, and to alter climate regimes, that is, to analyze the response of a watershed under climate change scenarios. The main difference between a rainfall runoff model and a hydrological model is that the former is aimed at determining streamflow responses, without further interest in other hydrological variables, while the latter aims to fully understand all the processes in the hydrologic cycle. The most general way to solve rainfall runoff models would be to use spatially distributed numerical simulations to the complete equations of saturated and unsaturated subsurface and open channel flow. More practical, physically based models commonly represent a watershed as a collection of hill slope strips on which simplified representations of the appropriate mechanisms operate. However, some of the most commonly used rainfall runoff models are based on conceptual and empirical relations that appear to give reasonable results. A watershed is a physical body subjected to natural laws that drive the behavior and interactions of all the parts that constitute it. Under this perspective, a watershed is a very complex natural structure that may need very detailed information to capture its functioning. In rainfall runoff modeling, the perspective is usually changed, and a watershed is considered to be a simplified system, like a black box, that receives inputs in the form of rainfall hydrographs and produces outputs, response hydrographs, without a detailed consideration of the processes that transform the former in the latter. Under this system's approach, we shall keep some points in mind. First of all, we need to fit the black box with a hydrograph that represents only the portion of the rainfall that will appear as response hydrograph. That is, the hydrograph must represent the effective rainfall, or at least the black box should provide some procedure to determine effective rainfall from total rainfall. The hydrograph produced only accounts for the event flow, so it is the response hydrograph. Base flow must be determined by some other way. However, as you know, base flow does not change much during any given event, and therefore base flow may be assumed to be a constant addition for all the duration of the response hydrograph. The system's view normally relies on graphical hydrograph separation methods, since we need to decompose total hydrographs into base flow and quick flow hydrographs in order to design and train our black box to properly reproduce the observations. A very important point is that the total volume of precipitated effective rainfall must equal the total volume of response hydrograph. Water cannot disappear, and by definition, the effective rainfall is the water that will appear as a response hydrograph, and then both volumes of water should be equal. Finally, the system's view, or the black box approach, is normally based on reasonable assumptions more than in physical process considerations. This is due to the fact that physical laws tend to apply to small elements of the natural system. Think for instance about infiltration models that only describe the process at small scales. Infiltration at the whole watershed scale may not be properly represented by those equations. Therefore, when considering the watershed as a whole, we need other forms of our mathematical expressions that may not be easily obtainable. Summarizing, for the system's view, we need to determine two procedures. one to determine effective rainfall from total rainfall, and another one that allows us to determine runoff or river discharge as a function of effective rainfall. The problem of determining the model structure and the values of the controlling parameters is what we call system identification. The processes with the longest residence times have a stronger control over the shape of the hydrographs and thus must be considered first when designing the model. Normally, considering the two processes with the longest residence times provides a good approximation. After having decided a structure for the model, two procedures must be followed to determine the value of the parameters. The first procedure is calibration, in which the model parameters are changed and adapted to try to best reproduce the observed time series with the model. Once a best set of parameters has been determined, its overall quality is determined by validation, which is the process in which a new time series, different from the one used for calibration, is reproduced with the model, and the differences between the observed and the model time series are summarized by means of some statistic. It is very important to use different data for the calibration and the validation processes. The calibration process serves to make the model produce outputs that follow the real behavior of the watershed. The validation process serves to measure the quality of the predictions made by the model. As we have already mentioned in previous lessons, effective rainfall is the total rainfall minus the losses. That can be classified into four main categories. The fraction of water evaporated during the event, so rainfall that does not even get to touch the ground surface, the interception that accumulates on vegetative surfaces, the amount of water that gets stored in the surface, mostly in ponds, and the net addition to soil water storage, that is, water that infiltrates into the soil. The first component tends to be negligible. The second and third components are usually small also, and therefore they tend to be included into the fourth component. There are different approaches in this case, but normally this is what happens. So everything is modeled as if it was accounted by infiltration, although we know it's not the case. Therefore, the ratio of effective rainfall to total rainfall is mostly controlled by infiltration. That is, infiltration is the main loss that reduces total rainfall, and thus is the most important process that controls the generation of runoff and thus streamflow. The most general methods consider the losses generated by interception and infiltration. The infiltration losses can be computed with models that we already know, like the Green model, for instance. But in a sense, all models assume some decreasing effect of the losses to account for the effect of the filling storages. In general, this complex combination is simplified in many models, like the Soil Conservation Service curve number method, where two losses are considered. One concentrated on the beginning of the rainfall period, which is called the initial abstraction, and a continuous one, the continuing abstraction, that is mostly due to infiltration. Now, we will introduce three simple rainfall runoff models. The first one is the rational method, used for a small and inexpensive drainage structure in urban areas or constructed environments. The second one is the Soil Conservation Service curve number method, which is more general and can be used for more serious hydrological modeling in urban and rural areas. And the last one is the unit hydrograph method, that is normally used for large watersheds. The rational method postulates a proportionality between peak discharge and rainfall intensity. This proportionality is expressed as the peak discharge being equal to the product of the effective rainfall intensity, IF, the area of the drainage basin, H sub D, the runoff coefficient, C sub R, that captures the effect of infiltration. Indeed, the smaller the coefficient, the larger the effect of infiltration, and a unit conversion factor, U sub R, that will depend on the units with which we operate. This unit conversion factor does not take any specific value. It is there to remind you that you need to pay attention to the units that you use. The rational method is a simple and flexible method that allows to approximate the peak of the hydrograph, but not its shape. We normally derive the effective rainfall from an IDF curve, and thus we assume that the return period, the frequency of the computed peak discharge, is equal to the return period of the generating rainfall intensity. The curve number method is the most widely used rainfall runoff model for routine design purposes in the United States and in many other parts of the world. It is a very complete method that provides a way to determine effective rainfall from total rainfall, runoff from effective rainfall, and the peak discharge. It even provides a bell-shaped average hydrograph that we can use in our applications. The method provides lots of tables to represent most situations, and for this reason it has been widely applied everywhere, although it is especially easier to apply in the US, where the input information is already collected in the format required by the model. Effective rainfall, capital WF, is computed by a simple formula that involves total rainfall, capital W, and the watershed storage capacity, Vmax. This storage capacity is related to a property of the basin that is called the curve number, the relation given by the expression in the lower part of the slide. It is very important to remember that this formula is designed to be used with inches as the unit for rainfall. The curve number plays a role similar to the runoff coefficient in the rational method. It summarizes the main characteristics of the watershed and provides a measure of the total infiltration. The larger the coefficient, the smaller the infiltration, and therefore the larger the runoff generation. Curve numbers depend mostly on two characteristics of the watershed. The first one is the soil type, that is characterized into 4 different types, A to D, depending on the infiltration characteristics of the soil. On top of that, the other characteristic determining the curve number is land use. The land use may have different nuances, especially for agricultural land, where infiltration may be different depending on the cover type, the cover treatment, and the hydrological condition. As you can see, the curve number is given in tables, where we enter with the characteristics of the watershed under study. There are tables for many different kinds of watersheds. The previous one and this one are for agricultural soils. We find tables for rangelands, we find tables for urban areas, etc., etc. Curve numbers represent homogeneous parts of a watershed, but as you may imagine, many real watersheds are a combination of these basic types. The curve number of the complete watershed is normally computed as a weighted average of the curve numbers for each basic type, where the weights are proportional to the area covered by each type. Curve number may also be adjusted to account for the amount of soil moisture that was present in the soil at the beginning of the event. The tabulated curve numbers correspond to what is called the average antecedent moisture condition, AMC, also called AMC2. These conditions correspond to an average occurrence of precipitation over the watershed. If it has rained more than average, the curve number should be adjusted to account for the increased amount of water stored in the soil, what is called AMC3, and similarly for the case of drier conditions, which is known as AMC1. The adjustment may be carried out using the formulas shown in the slide or by means of the table, which is only a pre-computation of the values given by the formulas. For the computation of the peak discharge, the curve number method assumes that the hydrograph is a triangle. Its height is equal to the peak discharge. Its base is equal to the time base, which is 2.67 times the time of rise. That in turn is the sum of half the rain event duration and 60% of the watershed time of concentration. Equaling the volumes of rainfall on the hydrograph, we obtain a formula for computing the peak discharge as a function of the effective total rainfall, the drainage area, and the time of rise. This computation allows to work with a triangular hydrograph. If we require something more evolved, the curve number method also provides a non-dimensional hydrograph with a duration of 1 unit and a peak discharge of 1 unit. Multiplying the x-axis by the time base and the y-axis by the peak discharge, we obtain a hydrograph for the event. The last rainfall runoff method that we are going to cover in this lesson is the unit hydrograph method. A unit hydrograph is a hydrograph that corresponds to a unitary effective rainfall. normally unitary in volume, a total volume of rainfall of 1 unit, but in some cases it may also refer to unitary intensity. And the unit volume corresponds to this unitary effective rainfall, but that lasts for a given time. Therefore, a unit hydrograph is always linked to a given duration of the storm. A unit hydrograph represents the response of a given watershed to a unitary rainfall event of a given duration. Why is this important? Because we can always decompose any storm into n substorms of a duration equal to the duration for which the unit hydrograph was computed, and then we can compute the total hydrograph by assuming unit hydrographs, each of them multiplied by the total precipitation, or the corresponding intensity, for every substorm. The unit hydrograph method assumes that watersheds respond linearly, that is, that if precipitation is double, discharge is double, which tends to be a better approximation for larger watersheds than for smaller watersheds. The unit hydrograph may be computed for a given watershed, as the response of every watershed may be different. To do this, we can collect many hydrographs for a given watershed and then a storm of a given duration. All these hydrographs would be similar, but not equal, and if we average them, we obtain the most representative hydrograph. We divide the hydrograph by its total volume, and we obtain the hydrograph for a unitary volume of rainfall and for a given duration of the rainfall event. As we have said, the unit hydrograph is only valid for an event of a given duration. However, further hydrographs may be derived. For instance, if we have the unit hydrograph for a storm duration of 2.5 hours, we can sum two of these hydrographs, the second one displays 2.5 hours obviously, to obtain a hydrograph for a 5-hour event. This new hydrograph would correspond to a rainfall of 2 units, and thus, if we want to obtain a unit hydrograph from it, we should divide it by 2, obtaining the unit hydrograph for a 5-hour rainfall event. In many cases, it is very complicated to obtain enough information about a watershed to determine its real unit hydrograph. For this reason, many authors have developed synthetic hydrographs that can be used to approximate the unit hydrograph for any given watershed, given some of its characteristics. Among them, the most important may be the linear watershed instantaneous unit hydrograph and the geomorphologic instantaneous unit hydrograph. With the unit hydrograph, we have finished this fourth and last part of the lesson. In it, we have presented what rainfall runoff models are. We have shown that the computation of the effective rainfall is a key procedure in the application of rainfall runoff models, and we have presented 3 simple models that are widely used in engineering practice. With this fourth part, we finish the lesson on runoff and streamflow, and we can continue with the exercises.